Hello everyone and welcome to this part 2 about the long short-term memory, where we're going to see the math behind this network. So let's get started. The objective is of this video is that we're going to understand how we will pass the data through the three different gates, the forget, input, and output gate. And then we will compare the prediction to the true value. Then, as usual, compute the loss. We do backpropagation. In this case, we will just do one. And then we update the parameters. All of this is considered one training iteration, which is something that we know. Okay, let's start by setting up an example. We have a time series of the values 1, 2, 3, 4, and we want to predict the next value, which is 5. So we will have as an input 1, 2, 3, and 4, and we wish that our network would predict a value of something very close to 5 or 5 itself. So we will do only the final time step where we input 4 and get 5. We have input for previous hidden state is 0.5. That was calculated using these three inputs. And the previous cell state 0.8. And we'll compute the next hidden cell state and the predicted value. These are the formulas. I only made the screenshot because I was too lazy to write them myself. So this one here, it's for the forget gate, where we will multiply the weight and the bias by the input. Only the weight, sorry, by the input and the previous hidden state. So this hidden state multiplied by weight, this input multiplied by weight, then they're summed together, and we will add the bias, this one, and then do the activation function sigmoid, which it is this part. Next, this is for the input gate. This is the first part of the sigmoid activation function. Again, it's weight of the input and this weight summed together plus bias, and then we do the activation. This is the tan-h, the second part. For the context of what each gate does, please refer to the previous video. So again, weight, bias, activation function, pretty standard. And now we're here at the output. And then, then we multiply them together and add the previous one, which is this one multiplied by what percentage we want to keep. We get a value here. It gets added to this value that we have here. Goes all the way to the next cell state, which is this formula. For the output gate, it's the sigmoid function of the weight plus bias, and also this cell state would go here, goes down, activation function, and then multiply these two together to decide the percentage that we want to keep, and that would be considered the final output. That's why it's called the output gate. So this value should be 5, or as close as possible to 5 in our example. Okay, let's take it step by step, starting by the forget gate. We will assume that we have these weights and this bias. So we do the calculation input multiplied by the weight, previous hidden state multiplied by the weight, sum them together, and then add the bias. So this is first multiplication, second multiplication, and then we add them together. And finally, we do the bias. We get this value. And then once we do the sigmoid function, we get the value of 0.68. So we can say that we keep about 68 of the old memory. So this 68 would be here visually. Now for the input gate, it's also, we assume some weights and biases. These start random and then gets updated through the backpropagation technique. So input, weight, bias, and then we do the activation function. We get 0.79. So we can say that we'll allow almost 80% of the new information. For this part, we get this value, 0.93. This is the proposed new memory content. So 0.93 would be multiplied by our previous percentage of 79%. This is what we did here. And then we sum them by the, because this sum is this one, this part, it's this part, and this part, it's the, if we remember, it's this part, previous cell state multiplied by the output of the sigmoid activation function. So we get a new cell state of 1.279. So remember, it will go this way as a new cell state, and it would also go down for in the next gate that we're going to see. So this is what I was talking about. Again, assuming some weights and biases, we'll do weight plus biases for the input. This is the input for weights and bias. Then do the activation function. We get 0.755, so we can say that we'll keep 75.5%. And again, this part here is the activation function of the cell state 1.297, which we saw here, which is this value. Passing it through the activation, we get this value. And next, this part is this part. We do the multiplication of both of these values to get the final output, which we got like 0.647. Again, it's the model output. Remember that the actual output was 5 from the example, but we got 0.647, which is pretty far, but is expected as it's only the first iteration or step in the training process. So the model didn't do enough training to start understanding the data. So next step, we will calculate the loss function. The actual output should have been 5, but we got 0.647. We do the MSE formula, actual minus predicted squared. We have a very big error. The model is still very wrong. Okay, so now we'll do the backpropagation now. These are not real values. I will just like make a conceptual flow. So we start from the loss function, make the derivative with respect to the predicted output, and then this gradient would flow into the hidden state. It would then we go in an inverse direction to the both output and the cell gates. So yeah, it will go inversely with every like arrow here, until it reaches the forget input and the candidate memory. So we can say that like each gate will learn how responsible it was for the error. So after doing the backpropagation, assuming like many values here, so don't take this as correct calculation. We do the gradient descent, which is the new parameter, is the old one minus the learning rate multiplied by the gradient function. So if we assume a learning rate of 0.01, we get this new weight. An example of only the output gate, but we do this for every weight and bias we have in the network. So you can see that the weight is positive and increased from 0.25 to 0.337. So we can say that the weight increases to push future outputs higher, which is what we want to do because we want to get closer to 5. And then with the next forward pass after the update, the output gate will open more, we can say. The hidden state will increase, prediction would move closer to 5, which is what we're interested in. So this is an example. We started with I think 0.647, and then it will just slowly, step by step, get closer to 5. So this is one training step. So finally you can say that the long short-term memory learns by adjusting how much it forgets, remembers, and outputs based on the feedback from its mistakes. Of course, in real project we will use matrices, not just like simple numbers, but it's basically the same process. Also the same process as in any other neural network. So thank you for watching. Please leave a like and subscribe if you like the video.